Okay. In the last video, we looked at the old way, and I shouldn't really say the old way, but basically we assumed that the pulley was massless and frictionless. What if you can't assume that? Okay, so we got some answers for the acceleration of the system and the tension in the string. What if you can't assume that the pulley is massless? So, if the pulley has mass, it must have what we would call rotational inertia. It must have a moment of inertia. Okay, so if it has mass, it must have a moment of inertia. Therefore, it must be considered in the problem. Basically, the fact that the pulley has mass means that it's going to take some effort to rotate it. A massless pulley takes no effort to rotate. A pulley that has mass is going to take some effort to rotate, and you might think that might detract from some of our acceleration or our tension here. Something might change. So now what we have to do is not only do we have to sum the forces, but if we need this pulley to rotate, we need to figure out the net torque on the pulley as well. We can't simply sum the forces anymore. We must sum the forces and sum the torques. So we're going to need a net force equation, which we already have the two net force equations. Those actually aren't going to change. The free body diagrams are exactly the same, but we're also going to need a net torque equation. So the net forces, here's what I'll do. I'll kind of section this off here. Okay, I'm going to bring over the net force equations. Again, those haven't changed. We're not changing those at all. We're just adding something else in because we now have to account for the rotation of the pulley. F net x was T equals M2 AX. And for M, we had, F net x equals F1G minus T1 equals M1AX. And actually, I take it back. There is going to be a very slight change. It's not going to change the format, but now that we are accounting for the rotation of the pulley, we actually have to treat the tensions in the pulley, on each side of the pulley as separate. And you'll see why when we get through the end of the problem. But we're going to need to call this, so just to simplify things, we'll call this one T2, and we'll call this one, I already kind of wrote it, T1. Missed that I wrote it right there. Okay, so this ends up being T2 equals 2 MAX, and this ends up being, mg minus T1 equals MAX. All right, if we're going to do a net torque for the pulley, then we need a free body diagram for the pulley. That would look like this. Here's the pulley. That's a great circle, by the way. The pulley, we're told, well, not even so much that we're told, but if we go back up to this pulley, some things that would be important to know for the pulley are the radius and the mass. Let's just say the mass is m, the radius is r. The rotational inertia for any pulley is given by this equation, 1/2 mr squared. So that's going to be important. Here's the axis of rotation for the pulley, right in the center. Now, we know that it's, if you look, this thing is kind of, it's supported, and we can assume that it's supported kind of right at the center part. So we're going to say that there's a force, almost like a normal force going out in this direction. The pulley has some mass, so the center of mass, let's assume, is right in the middle of the pulley. So let's say that there's a force of gravity downwards like this. I'll do FGP for force of gravity on the pulley. And these strings, the tension, or the The strings that cause the tension are coming off of the right-hand side of the pulley and the top of the pulley. So this one down here is the tension. Let's see, that's on M. I said that was T1. So we're going to call this T1. And we're going to call this over here T2. We need an axis for this, and normally we say that counterclockwise rotation is positive, but think about what's going to happen if we let the system go. M is going to go down, 2M is going to go to the right. That's going to cause the pulley to rotate in a clockwise fashion. So here we're going to break our convention. We're going to say that clockwise rotation is positive rotation. We need to sum up the net torques. Net torque must equal the torque, let's see, T1, that's going to be a positive torque. T2, that would tend to rotate it this way. That's going to be a negative torque. And look at this, the net torque from the normal force the torque from the normal force and the torque from the weight of the pulley itself, both of those forces act at the axis of rotation. Therefore, they do not cause torques. This is it for my net torque equation, equals I alpha. Now what we're going to do is we're going to write out the formula for the torque here so that we can solve, and then basically what's the reason that we have to do this. Let's take a quick step back. Okay? The reason we have to do this is because we can no longer assume that the tensions are the same. And here's why. If these tensions were the same, they would cause the same amount of torque, and therefore we would have no net torque, and that this pulley would never change its rotation rate. Well, that doesn't make sense. You can't have M accelerating and 2M accelerating and this pulley just going at the same rate the whole time. The pulley has to have an acceleration. So in order to have an acceleration, we need a difference in these torques. So cannot assume T is constant because that would lead to no rotational acceleration to match the acceleration of the boxes. So let's figure out how big these torques are. Both of these torques act a distance of the radius of the pulley away from the axis of rotation. So R1, T1, sine theta 1, minus R2, T2, sine theta 2, equals moments of inertia for a pulley, which is basically a flat disk, 1/2 mr squared, times, and there is an equation for alpha that I'm going to sub in right now. The equation for alpha we're going to sub in is alpha equals the acceleration divided by the radius, the linear acceleration divided by the radius. You'll notice what this does is it gives me r squared up here and r on the bottom. One set of those r's can cancel out. Let's go back to the torques. These r's are the same. We know it's the radius of the pulley. So this is going to be r, T1. And then the sine theta part, r is here, T1 is here. That's definitely a right angle, so sine of 90 degrees is 1. Same thing for the torque from T2. Minus r T2, but this sine theta term goes to 1, equals 1/2 mr A. And this A, this linear acceleration, is going to be the same as the acceleration of these objects. Okay? The angular acceleration is related to the linear acceleration. The angular acceleration, or the linear acceleration we're talking about, is the acceleration of the entire system. So this is this AX that we've been solving for in these other equations. Okay. Notice that I have an R everywhere. I can cancel those out. I'm left with T1 minus T2 equals 1/2 mAx squared. T1, if I do some rearranging, should be, let's see if I can fit it in over here. Bring T1 to the other side, subtract this back over. T1 equals mg minus max. So that's mg minus max minus t2, which is 2m ax, equals 1/2 max. Negative max minus 2 max is negative 3 max. Add that over to the other side, I get 3.5 max. Or, if you prefer, because I do, 7/2 max. So I have mg. Oh wait, I have m's in every single one of these. I can cancel out all the m's. So I have g equals 7/2 ax. If I want to solve for the acceleration, I simply divide by 7/2. I end up with the acceleration is 2/7 g. Let's compare that. We said that adding in that the pulley has mass might affect the acceleration because since it has mass, it has some inertia. It's going to be harder to rotate or to move the system. G over 3 is the same thing as 2g over 6. This is 2g over 7 now that we account for the mass. This is smaller. 2/6 is greater than 2/7. The acceleration has gotten smaller, just like we thought it would. I could even, if I wanted to, using this equation, let's see, the angular acceleration equals the linear acceleration over r. 2/7 times g times 1 over r. The angular acceleration turns out to be 2g over 7r. That might be something you want to calculate as well. The rate at which the angular velocity increases. Finally, let's go back and take a look at the tensions. Now that I have the linear acceleration, I should be able to go back and find those. T2 was given by 2m ax. T2 must be 2m times 2/7 g. T2 ends up being 4mg over 7. T1 was given by mg minus max. So this is mg minus max was 2/7 g. mg minus 2mg over 7. If I want to get common denominators, that would mean that this would be 7mg over 7 minus 2mg over 7. I end up with T1 equals 5mg over 7. T1 is slightly greater than T2, meaning that the torque from T1 is slightly greater than the torque from T2, causing rotation in this direction, which is what we want. And notice that the tensions are not the same, and they're very similar to this tension, but they're not quite the same. 2/3 would be like, let's see, why am I drawing a blank here? 4mg over 6. T2 is now slightly less than that. T1 is now slightly more than that if you take those fractions into account. So, the whole point with this is we have looked now at basically what I would like to call a second approximation. There's still factors that we have not taken into account, that we're not going to take into account in this class. But this is a good indication of what science is really like. Okay? Science isn't just, oh, this is the answer and that's it. There are differing degrees to which you are matching reality. Okay? At first, we neglected to have the pulley have some mass because you weren't ready for it. Now that we've done torque and we've gotten better at this, now we're going to say, what if the pulley has mass? That reflects reality more, and we see that we have answers that are fairly similar to what we got before, but also slightly better, slightly different. This second part that we've done is more in tune with reality, because in reality, you're going to have a pulley that has some mass. It's not going to be completely massless. The last thing I want to talk about, because it shows up on one or two of the homeworks, is gearing. And this is something I don't know a ton about, but this is a good subject to get into if you like making things. If you want to go into engineering of any kind, really, then you might be interested in this. Let's say that we have two discs, and those two discs are linked together by a chain. The chain is looped about both of them, so that it doesn't slip or slide. The disks have the same mass. And we're just going to make that M. So here's a picture of our disks. Little one here. It's got a radius of R. And a bigger one over here, which has got a radius of 2R. And these two disks are linked together with a chain that runs from one to the other like so. So the chain goes around this first one, to the second one, around the second one, and back to the first. And that chain does not slip. You might be interested in how their rates of rotation and their speeds compare to one another now that they're linked together like this. Before we can, and you might also be interested in their moments of inertia. Let's start with that. The moments of inertia equation for a disk is 1/2 mr squared. So the moment of inertia for the smaller disk is 1/2 mr squared. The moment of inertia for the bigger disk is 1/2 m2r squared. When we square 2r, we're going to get 4r squared. And then we multiply that by 1/2 m, we end up with 2mr squared. Now, how does that compare to the smaller disk? Well, you might be tempted to think it's twice as much, but look again. This coefficient is 1/2, this coefficient is 2. 2 is not just twice as big as 1/2, it's 4 times as big. So it turns out that the moment of inertia for the 2r disk is 4 times as much as the moment of inertia for the smaller disk, the disk with a radius of r. Now, as far as a comparison of their rotation rates and their speeds, we need to remember the following fact. The linear speed, v, of the chain must be equal at every point. The speed of this chain as it goes around must always be equal at every single point. Why? Because otherwise you would have the chain slipping and sliding. You would have it bunching up in some places and then sliding along the disk in other places. That's not what happens. This chain must have the same speed at every single point. So what that means is the linear speed of the chain is the same everywhere. V is the same everywhere. That means for a point on the outside of this disk and a point on the outside of this disk, those points are moving at the same rate, linear rate v. Vr must equal v2r. Now remember, we have this equation that tells us the linear speed is related to the angular speed by, take the angular speed, multiply by the radius. That tells us that r times omega of the smaller disk equals r times the omega of the bigger disk. But r for the bigger disk is twice as big. So it's going to be 2r times omega for the 2r disk. I can cancel the r's on both sides, and what I end up with is omega for the bigger disk is half of the omega, the angular speed for the smaller disk. That kind of makes sense. If the chain is not slipping or skidding or sliding, then the v, the linear speed of the chain, has to be the same everywhere. Then that means that the points on the chain is moving the same speed each way, but because this is such a smaller disk, it's got to rotate faster. Okay? Omega r has got to be greater than the omega, the angular speed for this disk of 2r. So that makes sense. To get the angular speed for the bigger disk, take the angular speed of the smaller disk, cut it in half. This has to rotate much faster in order to provide the same v. This, because it's bigger, does not have to rotate as fast. And as a matter of fact, it's the same result for the acceleration, if there's any acceleration. The angular acceleration for the bigger disk is equal to the angular acceleration for the smaller disk divided by 2. And again, the 2 comes from the fact that the radius was twice as big. Again, I don't know too much about gearing, but that is something that comes up comes up once or twice on the homeworks, so I just wanted to point it out. Okay, it is an interesting topic, something that maybe you could look into if you're interested, especially if you're interested in building things, engineering, stuff like that. That's it for torque and rotational dynamics. You'll see that a lot of the problems that we do in this little mini unit are very similar to problems we've done in the past, but with the added twist that now we have something rotating with mass that we have to account for. That's where the difficulty comes in. There's a lot of stuff in this unit that's very similar, but now we just have to apply what we know about torque and rotational kinematics to these familiar situations to get answers that are more in line with what really happens in reality. Okay? We're not saying that this is bad. It's just not going to be quite as accurate as this, most likely. Okay? In a lot of cases, we can just get away with doing this. But if we want to be really accurate, we got to start going towards this. That's it for this video. Our next little topic will be on rolling, and I will talk to you then. Bye.